So here's a quick check. Are the following elements, compounds, and or mixtures? So it could be more than one, right? Take a second, classify each picture. Is it an element? Is it a compound? Is it a mixture? So pause the video, take maybe a minute or two, see if you can figure these out. Okay, so for this first one, it is not elemental, right? There are elements in these, but they are compounds, CO2. But it's just CO2, so it's a mixture, or sorry, it is a pure substance, not a mixture. So compounds, pure substance. This is CH4, right? Both of these are the same. This is a compound as well, different elements bonded together, not a mixture. Again, compounds, right? COH4. It's the same thing, so it's not a mixture. Here we have two different compounds, NH3 and CH4, which means we have a mixture of compounds here, right? Two different things. Here we have two chlorines bonded to themselves. So these are elements, right? They're also molecules, which was not really an option here, but they're not compounds because they're not different from each other. So we call this elemental chlorine. And it's not a mixture because there's not something else in here. Here we have a bunch of sodium atoms, seemingly like in a lattice, in a solid state. So this would be elemental sodium, not a compound, not a mixture. Here we have NH3, right? This is a compound, but there's nothing else here, so it's not a mixture. Here we have NaCl, or salt, sodium chloride. This is a compound, two different things, not a mixture. This is two different elemental forms, right? Oxygen bonded to itself, elemental oxygen, and nitrogen bonded to itself, elemental nitrogen. But it is a mixture, right? So it's an elemental mixture. Two different things. This is kind of like our atmosphere. It has a bunch of nitrogen and then some oxygen in it. These are hydrogens, elemental hydrogen. So this is element, not mixture. Element, right? Oxygen. Element, this is nitrogen. Compound, right? This is a mixture of both elements and compounds. And then this is a mixture of compounds. So hopefully you're able to discern what each of these were and figure them out. So now we're gonna move on to 2.2. 2.2 has a bunch of stuff in it, so we're just gonna do the very first part of this, but it's kind of continuing talking about these things, atomic structure and whatnot. So the atom, right? We've talked about the atom and elements. Now let's talk about what's inside an atom. So the atom is the basic particle of chemical elements. For example, carbon is made of carbon atoms, right? Oxygen is made of oxygen atoms. We saw that. Atoms consist of subatomic particles. Subatomic, right? That means below atomic or smaller than an atom. And they are protons, neutrons, and electrons. The protons and the neutrons hang out in the middle. We call this the nucleus. It's in the center. And then electrons are arranged around the nucleus. They orbit around the nucleus, and they are arranged in different energy levels. So some electrons are seemingly closer or farther away, depending on their energies. So this is the atom, the three special parts of it. You should know where each part goes. Each part of the atom has a relative charge, right? Protons are positive, right? P, proton, positive. Neutrons are neutral. They have a charge of 0. So protons are +1, neutrons are 0. And electrons are negatively charged. So they have a charge of -1. And this is a relative charge. They're all relative to each other. So an electron has the same strength of charge as a proton. It's just negative instead of positive. If we wanted to talk about electrical units like coulombs, they are not 1 coulomb. it's very different. But in chemistry, we're mostly concerned what they are relative to each other. So we talk about them as having relative charges of +1, 0, and -1. Their masses. So mass, you can think of mass as similar to weight, right? Protons have a relative mass of approximately 1 AMU, atomic mass unit. So this is a special unit that's again relative to the other things, right? Protons and neutrons both have masses of 1 atomic mass unit. If you want to know what it is in kilograms, it's like something times 10 to the -17. It's super tiny, right? But electrons have an even smaller mass, um, one 1 over 1,837 AMU. So electrons have such a tiny mass that when we start doing mass calculations, we say it's negligible. So sometimes you might see this as 0 mass. That's not technically true. They do have a little bit of mass, but it's so tiny it doesn't really come into play when calculating the mass of a given element or atom, right? So, which subatomic particle is responsible for chemical bonding? Which subatomic particle is responsible for chemical bonding? You could say they all are, which there is truth in that, but one of them plays a much bigger role than the other two. And my example is these particles are shared or exchanged during chemical reactions. So you have three options, right? Protons, neutrons, electrons. Um, Looking at a picture might also give you a hint. Take 30 seconds. Discuss. Write down what you think in your notebook. Okay, the subatomic particle responsible for chemical bonding, I'm going to go back a slide, is the electron, right? These things are densely packed into the middle of the atom. There is actually a bunch of empty space, like a crazy amount relative to how big these things are. And then the electrons, they have a tiny bit of mass, but they have lots of energy, so they're flying around out here, right? So these are the things that are getting exchanged or shared during chemical reactions and chemical bonds. So we are going to be very concerned about what electrons are doing as we learn more about the atom in chemistry. So one last little bit before we're done for today. When you look at the periodic table, it gives you a bunch of information, and we need to know how to interpret this information. So the atomic number is usually up at the left or sometimes above, right? And this atomic number, sometimes we use the symbol Z to represent it, and it tells you how many protons there are in your element. So carbon, this is its elemental symbol, here's its name, has 6 protons. That is its atomic number, 6 protons. The number of protons is also equal to the number of electrons in that atom, and that's if it's neutral, right? So carbon has 6 protons and 6 electrons. There are things we can do to change the amount of electrons, but 6 protons is carbon. And it is always going to be the smaller of the two numbers on the periodic table. This number is something else, which we'll talk about in a second, but what subatomic particle defines what element a substance is? Take a second, think about this. What subatomic particle defines what element a substance is? You have three options. Okay, so the subatomic particle that defines an element is the proton, right? We just talked about it. 6. This is its atomic number. Go back here. Protons are in the middle. However many you have defines the element. So 6 protons is always carbon. 1 proton is always hydrogen, right? We can't change that. That's what defines what our element is. My second question is, why are elements defined by their number of protons? So think about this, perhaps discuss in class, take a minute. and then I'll talk about it. So let's go back to our picture. Think about this. Protons, neutrons, electrons, right? We already said electrons are involved in chemical bonding. They are tiny. They are on the outside. They can be lost. They can be exchanged. They can be gained, right? So it wouldn't really make sense to define an element which we want to be like the basic building block using electrons because they change so much. Neutrons, right? They're neutral, which means they are not attracting the electrons. They're not doing a lot in terms of the electrostatic forces within this, which are the big forces that are acting on other elements. They are in the middle, which is important, right? But the protons are also densely packed in the middle. So these things do not change easily within an atom, right? Electrons, it's easy to take or give electrons relatively, right? But these things are much, much, much harder to change, right? And protons have a +1 charge, so they're the thing that is interacting with these electrons, right? And it turns out that the number of protons you have defines your chemical characteristics, right? So that is why they end up being the thing that define an element, right? Neutrons are important, we'll talk about them, but within a given element, the other two things can change. The amount of those can change, but the amount of protons is what defines the element. So here's a couple representations of two different elements, right? We can see helium has 2 protons. It can have various amounts of neutrons, and then it's going to have these electrons on the outside too in this case. Lithium has 3 protons. It's the next one on the periodic table. It's got some neutrons in there, and then it's electrons floating around. These models are useful because we can see how many of each thing we have. You can see, get an idea of where the electrons are as well. So that last number is the mass number when you're looking at the periodic table. It's down at the bottom. It is bigger. In this case, you can recognize it's almost twice as much. And the mass number, this is the relative atomic mass, is a rounded number that gives the average atomic mass within a given sample of that element in those atoms, right? So we say it represents the total mass of the atom. We're kind of ignoring electrons here. And it is represented by the symbol A, right? This is Z, this is A. And it is the larger of two. If we think about carbon, most carbon atoms, well, all of them have 6 protons, and most of them have 6 neutrons, right? If you add those up, you get to 12, right? So the number of neutrons equals the mass number minus the atomic number, right? So 12 minus 6 is 6. That's 6 neutrons. And this is actually an average of all the possible carbons. So there is carbon 12, there's carbon 13, carbon 14, and it's an average. So almost all carbons are carbon 12. There are a few that are carbon 13 and 14, and so that's why this number is not perfectly 12, right? Because it's an average of all those within a given sample. Phosphorus, right? Same idea. Phosphorus has an atomic number of 15, and its mass number, or its relative atomic mass, is very close to 31. Remember, this is an average, right? So the average phosphorus atom, the most abundant one, is going to have 16 neutrons, right? Because 31 minus 15 is 16. So this is a very important number as well. And that is all we're going to do today. You have an assignment that you're going to work on. There's also some extensions, so I'm going to post some extra things if you are interested in digging a little bit deeper into these ideas. I know we're still kind of reviewing and revising, but I want to give you the option to look deeper if you're interested in that. So I'll post a couple things on ManageBack for that as well. But I hope you have a good rest of your day.